Good evening, sir. Good evening, everyone. Yeah,
Good evening, Anand.
good evening.
So,
We should
uh,
wait for a while or what?
so let's start. Even
Not yet. Not yet 8 actually, so maybe we can.
yeah. So uh, even yeah, this much audience is enough. Even Anand, and also our audience is on YouTube. So I have seen the that this channel 48
Okay, 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 okay.
now. I've subscribed. So no issues now. We can, even if less audience is there, we can proceed. So we have now.
Yeah, no problem. We can. Okay.
Okay, so let me a brief intro you then about this Pi Square seminar also.
Sure.
So hello everyone, myself Suham Maurya, and this is the seminar. Already we have 3 seminars. This is a Pi Square seminar series. In this series, like this is a kind of place or in a forum, a kind of you can if you are interested to give some talk or or of any kind. If it is not only I have started it for mathematics, but now it is I reached the area. Now it could be any kind of any area. It could be it could be for data science, ML. Okay, and also if you want to it could be a application or whatever the data science area, AI, ML, whatever the area you have, whatever whatever you are thinking to, this should be shared to all other students should know.
Mm-hmm.
So then you can this is a place you can be here. You just contact me. I have already created a G space. I am spreading out this G form each time. Okay, with the mail, you can fill out. You can reach to me, and my core team is there. They will help you to in the creating the slides. Also, just tell us your idea. So that's the Pi Square seminar, and today we have a talk who is going to present by Anand. He is our diploma student and also core team member of us,
Mm-hmm.
our this Pi Square seminar. And the topic is Anand. You can tell the topic also and proceed with this talk.
Yeah. Okay. Good evening to everyone. I hope I'm audible clearly.
Yes.
Yeah. So basically, my name is Anant Kumar, and I'm a diploma level student. This today's topic or today's presentation basically is based on some of the mathematical curves that I find very fascinating. Actually, it is kind of an area which is not very much explored, and further because of the advent of maybe calculus, for example, or nowadays computers are there. So the very geometrical identity of these curves, they are kind of lost. We can basically think of, I mean, nowadays these curves are thought of as if they are just graphs of some equations, right? That is what I mean, kind of they have been reduced to, but they have a rich history. And when, for example, calculus was not there, and a lot of computer software is not available to us, then many of these graphs or these curves rather, they could be drawn with very elementary geometry. So my stress today, whatever curve I discuss over here, will be from the point of very fundamental geometry. So assuming that you can, I mean, all the instruments of a instrument box, like a set square or a circle or a compass, for example, that should be enough to, look at these curves and see some, a bit of history about them as well, right? So I hope that you will be able to, get to know about these curves, though they have been lost, but at least we can at least know the names of these curves, and maybe if you get some time, you can explore, right? My emphasis today will also be on one more thing. I would be using GeoGebra as a tool. Actually, I'm going to use GeoGebra as a tool, and that I can at least show you exactly some of the things that we could actually do with this particular software. Actually, it's a very useful tool. Okay, so let us start then. The presentation, first of all, I think I will not be able to see the screen. So just a moment, I will.
Yeah, in between. So as I have been listening this topic, so I think it's really interesting. And also, many of you don't know the GeoGebra, but this is a tool here. You can see the visualization of any like curves or plane. This is a 3D. There is an
Mm.
option of 3D, 2D. So you can see there. So that's a good thing that Anant is going to use it. So you will all of you learn also. If you heard already, that's good. If not, then you can see it here.
Actually,
Thanks,
found
Anant.
it to be very useful in machine learning fundamental courses. For example, I'm say how to visualize the transformation of matrices and other things actually, right?
Yeah.
In any case, so let's say we just let me present the screen. What we're going to have is, yeah, the presentation should be visible.
And also, I will be sharing a
Seem to
feedback
give any
form. So
indication.
I will ping in the chat. And this is a request to all of you that try to fill that feedback form so that we know if you give us some suggestion, we can take the suggestion, we improve ourselves, so that this will be a good forum place where all of you students can uh, uh, share their knowledge and get their knowledge. And also, who is going to present actually get a certificate also as a presenter from the Spice Square seminar team. Okay, go ahead, Anand. Yes.
Well, extremely sorry, sir. Seems like my computer just crashed actually. Just give me a few minutes, okay?
Yes, yes.
It's a very embarrassing, but then what can be done?
Okay, so issue got resolved, Anand. You are on mute. You are on mute.
Yeah, I just started by the way. I think it's too heavy for this, it seems. Entire thing crashed. Anyway, so let me just give the presentation at least. I'll cut short through of some of the things basically because the time is going to go away over there. Right.
Even if you have some history thing, you can just orally tell. Then once your computer will
Yeah.
ready, then you can present.
No issue. Now I think the presentation will be up, by the way.
Okay, yeah.
Yeah. Okay. So basically, we shall be looking at some of the these mathematical curves, as I said already. Let's look at a bit of history, for example. Now, mankind, as you know, has been fascinated by curves and curved shapes long before they were regarded as mathematical objects. Actually, right? For evidence, one has to just look at some of the prehistoric ornaments. For example, the left one is actually a piece of like a belt. Actually, it was found. Uh, it was way back. Actually, it belongs to like 500 to 700 BC. Actually, while the right, if you see, that is one of the a figurine from the Indus Valley civilization, and you could see this the intricate trefoil that is in the shawl of this person. Actually, on the left side you could see the spiral that's going on over here, right? So that's indicated actually at least that the curves were definitely kind of in the minds of people, right? They're fascinated by them. Okay. However, geometrically, the way that we define the curves as contours over here, they actually were studied first and documented by the Greek geometers, right? Uh, Normally or gradually, as the shift of interest took place over here, some of the idea of the concept curve or geometrical concept as a curve, and it gave way to analytical aspect of the curve as being a graph of the function. So the loss of individuality is what we find over here. Some of the very famous curve were basically lost, right? So we are going to just review or visit a few of them. So the first one we take up is one of the very, uh, a very famous or kind of very familiar curves to us, which is a parabola, right? A parabola, the diagram shows in blue a parabola and its evolute, which is in red actually. Now we shall see what evolute is in a minute, by the way. Now, first of all, the construction. Now, how it can be geometrically constructed, right? For example, we already have seen a set square in our instrument box, right? So how many of you thought that we could use the set square to draw some kind of curves, by the way? Because I, at least in school, I never thought that set square could be used anything else apart from drawing line parallel to something or at right angles, for example, right? However, found out, or at least it turns out, that we can actually make use of the set square to actually draw a parabola, or at least get a parabola, by the right. So first of all, we have a fixed line AY and we mark a fixed point S, but that is not on the line actually. So we separate from there, right? Now, if I place a set square, which I have named as UQV, which is right angle at the point Q with the vertex Q on the line AY and the side QU that passes through the focus. That is a mandatory thing, by the way. We need to have this side QU passing through S always, right? So if I just now draw this line QV, which is the other edge, okay, I just draw this line QV, which is the other edge over here. Now, if I keep on repeating this procedure, so what I have to do is I have to always make sure that the right vertex Q is on the line, while one of the edges, QU, it passes through the focus, the fixed point. This is not yet any tool by. This is just a bit of drawing that I've drawn over there. I'll explain in a minute. Okay, let me come to the end. Okay, so what happens now is if I repeat this process a number of times, then what I get is a parabola, but that is obtained as the envelope of these lines. Actually, we shall see this in animation pretty soon over there. However, what exactly is the envelope? The envelope is actually nothing but if we have a family of curves, okay, there's a family of curves, which implies there's some curves which depend on a certain parameter, right? So a single parameter family is what I have. So if I have a family of curves, then the envelope of that family of curve is basically another curve in general, which is tangent to every member of this family at exactly one point, right? Or if you say conversely, you take any point on this envelope, you will find that exactly one member of this particular family is touching the curve at that very point over there, okay? Now let us try to see this particular thing in an animation over there, exactly how we can get this. So just a moment, I'll have to switch in this case the presentation to the GeoGebra tool, right? So let us see exactly how it comes out to be. I will try to animate the whole thing. Effectively, I have already prepared the animation and we would like to, look at exactly. I'm basically animating in this case the set square as a triangle, this triangle that we have. The point S is marked over here, I could see that, right? And then this point M is rather the Q that we had in case of the diagram over there. So what happens over here is, as I move, in this case, the set square, making sure always that this point, this edge of the set square is going to pass through this point S, while the right edge, the right corner rather, is on this line. This line is what we have, a fixed line over there, fine. So we can animate the whole thing and we can see how exactly the parabola turns out to be. So let us see. The idea is to just always draw the lines through this edge of the set square, while the other edge, this particular vertex moves along this line, while the other edge always passes through S, right, the fixed point actually. So what we get is something like this. We have a series of lines coming up, and these lines, as you could see, is basically generating a certain shape, which is this particular shape. Let's do it again, put it up a bit above and repeat the whole thing. We can see how entire thing comes out to be. So effectively what happens is we get a certain curve. It looks like we are generating a certain, right now I haven't yet plotted any curve over there, but it turns out that it seems like we are going to get some kind of curve, right? And the curve actually is a parabola, which many of you obviously are familiar, that it can be represented by in a Cartesian form. And this new yellow curve that we have just drawn over here, that is the parabola itself, right? So again, going back to the presentation, basically this whole sort of thing is what I explained already. So this was animated in the whole thing, okay? I obviously didn't draw a set square, but at least this was the idea. If you do that, you can actually end up getting a parabola, okay? Fine. So now there are some properties of this parabola which actually are elementary and they should be familiar, or many of you are familiar with the whole thing actually.
So
Oh,
slide.
yeah.
Your page is now is switched. Okay.
Now it's switched. Okay. Sorry. So the parabola, as it turns out, can also be defined as a locus of a point P, which is over here, whose distance from a fixed point, that fixed point we usually call as a focus, while there's a fixed line which is called a directrix. And it turns out this parabola can be defined as the locus of a point that moves in such a way that the distance from the point S, which is the focus, and distance from M, they're identical actually. They must be equal, right? If we try to come up with such kind of constructions, also generate a certain parabola, right? Now, if we look at the Cartesian equation, normally this is one thing where people are familiar with. That is what we have in the higher secondary classes, 11th. The Cartesian equation can be obtained by looking at the coordinate system where the point A, which is kind of the midway between the, focus and the point Z actually. So if I take AS as the axis of the parabola, then this AS is in fact, the whole curve is symmetrical about this line actually. And turns out that we can actually have this property that Pn whole square, Pn is the ordinate which I draw from the point P onto the axis. That square is always equal to 4 into As into n. This is one of the very fundamental property. And if I am going to take As and Ay as the x and the y axis respectively, then the standard equation for the parabola, which we are familiar with, turns out to be y square equal to 4x, right? I mean, this is the standard equation that we know of actually. Okay. Then if I consider some other property, there's a very interesting property which we are actually going to see quite a lot over there, and which is being used in fact. There is a fact that if I consider the normal at certain point, normal is a line drawn perpendicular to tangent, right? So normal is basically bisecting the angle between the focal distance and the point between P and the length PM actually. This whole angle, the green one, is bisected by the tangent line, well, external angle, which is bisected by the normal, is basically this red one, right? So if you imagine that the ray of light comes along this point C and parallel to the axis, then after getting reflected, we already are familiar with the law of reflection, right? We know that the angle of incidence is equal to angle of reflection. So if I imagine the parabola as a mirror, for instance, in that case, the ray of light coming parallel to the axis will be, after reflecting, pass right to the focus, in fact. Okay, this is a very important property, in fact. Okay, this is in fact being used in the number of places and in number of application, by the way. This is in fact we also one of the useful thing in optics over there. For instance, we could see this whole thing once again. Just try to animate the whole thing. Just a moment. So what we can see is something similar to a reflection. So what we have is a reflecting property, right? What we consider is like this. So basically in this case, I have already prepared point P. Imagine there's a point P moving along. So imagine the ray of light which comes very slowly, like so. When it just comes over here, after getting reflected, it passes right through the focus. Okay, this is one of the very important property that we have for a case of parabola actually. And this property, as you shall see later on, will be utilized in a number of applications over there. Fine. So if I just go back, right? So if I consider, for example, the presentation, yeah, the same property, this parabola can also be thought of as being obtained by cutting a double cone, for example. There's a double cone actually, right circular double cone, and the parabola can be thought of as being obtained by intersection of this double cone by a plane, which in this case is this plane, which is over here, the plane number C actually. This is the parabola. I have also shown some other kinds of conic sections, which is what they were initially called as, and that is how they initially were studied actually. This C section is what the parabola is. B gives an ellipse, which will seem soon seen enough. A is nothing but a circle, and if I cut it a plane which is just perpendicular to the base of the whole cone, I get a hyperbola actually, right? These are the other conics that actually are generated by cutting this double cone over there, right? We are interested in this part, which is a parabola, which is obtained by intersection of this cone by a plane that is parallel to the slant length of the cone actually. Okay, as I said already, the reflecting property, because of that, headlamps and flashlights, they use parabolic reflectors where the bulb or the LED is located right at the focus actually, right? This is one of the applications we have. Similarly, for example, Newtonian telescope that we have, it uses a parabolic reflector to focus light coming from distant stars at the focus without chromatic aberrations. So in lenses, for example, if you look at the refractor telescope or the telescope containing lenses, for example, then they do suffer from a lot of chromatic aberrations, right? So these are absent in case of this mirror, where we have a parabolic reflector kept at this particular point actually, right? At the back of the whole telescope over there, fine. Similarly, the solar reflectors, for example, which are used to heat water or concentrate energy of the sun at one point, then the radio telescopes, for example, or a dish antenna that we have all seen in our houses, for example, They're all parabolic reflectors, in fact. They're technically paraboloids, which are nothing but a surface of revolution over there. But they all use parabolic reflectors, right? For example, in a dish antenna, the parabolic reflector is not actually symmetrical. So we take a part which is off symmetry so that the transponder can be kept right at the focus. Okay. Then the ray coming from the sky, which are satellite basically, they'll be reflected to that particular transponder over there, receiver basically. Okay, so a liquid, if you rotate, for example, take a bucket, turn it, rotate the water with your hands, for example, you'll find it takes actually a shape which is a parabolic shape over there, right? So this parabolic shape is there as well. So a parabolic reflector pointing upward can be formed by rotating a reflective liquid like mercury, for example, around a vertical axis. This makes the liquid mirror telescope possible. So we can have large telescopes actually able to gather a lot of light by using such kind of construction over there, right? Similarly, parabolic reflectors are also a popular alternative for increasing the wireless signal strength, right? Often we know Wi-Fi signal is, weak at some part of the house, for example, so they can be used to increase the wireless signal. Even if simple ones, for example, users have reported at least 3 dB or more gains over there, right? This is one of the application that we are. And finally, this is interesting thing, the Olympic flame, as we know, is traditionally lit at Olympia, actually, Greece. And this is actually used by reflecting the sun's light, concentrating the sunlight using a parabolic reflector. So it is a property of a parabolic reflector, which is to say that we just focus beam which is parallel to the axis right at a point. This is not the property of a spherical mirror, by the way. You should keep that in mind. Though in our schools you must have studied the concave mirrors, for example, which are actually spherical mirrors. The idea is that when the size is quite small, then the parabola and the sphere are hardly distinguishable actually, right? That's what the idea is. Now the other application, engineering, for example, suspension bridges and arch bridges, for example, they use parabolic shapes. Now they have very interesting property that if you have a parabolic shape, they will distribute the load uniformly actually. Or you might say in these arch bridges, for example, the load is distributed uniformly, and that is why you require parabolic hanging chains over there, right? Contrast this with a very interesting thing. For example, if you take a chain and just suspend it from 2 points so that it hangs because of its own weight actually, then the shape is not a parabola, by the way. The shape looks very close to parabola, but actually is known as a catenary over there. Fine. I haven't covered that in this particular slide at least. Okay, so that was a bit of history. For example, Euclid, he wrote 4 books on conic sections, by the way, but they all have been lost. Perhaps because they were very quickly superseded by the works of, I didn't write the name, but some person who was in 3rd century BC actually. And it was who named these curves? I think it was, I have to see exactly who the person was. Okay, it was basically Apollonius, by the way. See, so Apollonius didn't give the focus and directrix property. However, it was treated by Pappus of Alexandria, which was about AD 300. Okay, AD 300. Then the invention of the coordinate geometry that we often have in our school, the analytical geometry, basically, it was done by Descartes. And they basically put these curves of 2nd degree, put these shapes like parabola, ellipse, and hyperbola as curves of 2nd degree, right? But his work was extremely obscure and very difficult to go through that actually. Later on, Wallace was very young at that point, treated them as plane curves and free of cones. By this, it was the first time they were freed of cones basically, and we can study them independently, right? And by about the same time, Pascal, the Blaise Pascal, after which the name of the unit of pressure has been named actually. Pascal treated them as projections of circle, and that foreshadows the projective geometry, which will come later 200 years by the right. So he was the first to look at this curve as projections of circle, in fact. And about the same time, Galileo showed that path of projectile, which is launched obliquely in air, will be a parabola, and we already are familiar with that. In absence of gravity, in absence of air resistance, to launch any object will just follow a parabolic shape, right? And similarly, the reflecting telescope was suggested by James Gregory. It was in 1663 actually, and the first one was constructed by Newton in 1668, where he used this parabolic reflector. Okay, So that's about parabola about this. I mean, say there are a few more things, but we shall look at the next one. The ellipse, which is, these are some conic sections, which I'll just try to pass very quickly. The ellipse will be the second curve, which we'll be looking at. And this is shown in this particular red with the black circle, again, as the, this one was the auxiliary circle for the ellipse, actually. So first of all, the construction. The idea is to now draw a circle instead of a line that we draw in case of parabola. We now have a circle, okay, fixed circle, whose center is at the point C, and one of its diameters, which is ACA prime, is what I have shown over here. So mark a fixed point S on this particular diameter. Okay. Now you just now place a set square again. So we have this set square again coming up. The set square is placed so that the right vertex lies on the circle, and one of the edges must pass through the focus S, or the point S, which you're looking at, as we saw in case of parabola as well. So now we just draw the chord through the other edge, right, coincident with the other edge. Then if I again repeat this process a number of times, then the ellipse is obtained as the envelope of these chords, right? So again, we shall just look at effectively this whole thing in GeoGebra so that we can see the things in action and appreciate how this whole thing comes up over there. So let's see, this has been doing for a long time, so I'll just, we're going to look at, in this case, the construction of an ellipse, right? So let's see, we have over here this fixed the fixed circle with the diameter A prime and C being the center. Again, I'm not in this case showing the set square, but I'm just showing the other edge which is going to come up. Additionally, what I've done is I've just taken two such lines or two such set squares together so that I can actually draw them once in one go actually. So what happens is we have these chords, and you draw them, effectively they generate such kind of an envelope. You could see that there's no curve right now, but at least these lines, they actually show us, you can see starting from any point over here, they give a particular ellipse, right? And this indeed is an ellipse that will be verified by actually looking at the equation of the curve, which I think many people are going to be familiar with. And the relevant equation that we are plotting right now is this red curve over there, right? So you can see that this red curve is being generated as the envelope of all these chords over there. Okay, so that is what an ellipse is and how it can be generated. Now going back to the presentation, there are again some of the properties that we should be familiar with, though there are many properties, and if you are actually going to be interested, you could actually go look at any say treatise on this kind of conic sections. They are enough present. From my side, I have tried to collect some of the more interesting or at least common properties that we have. So first of all, some terminologies in this case. A prime that we have, that is referred to as the major axis of the ellipse, the biggest diameter, and a chord which is BCB prime through the point C, perpendicular to A prime actually, that's called a minor axis, right? The amount by which the ellipse deviates from the auxiliary circle is measured by the ratio CS is to CA. So that is this length CS and CA. The closer the point S is to the point A, the greater is the deviation. So if I make this distance A is small enough, the deviation from the circle will be large actually, right? That is, this ratio is referred to as the eccentricity, which is a number which is less than 1 actually, right? Eccentricity of the ellipse is actually measuring exactly how much the difference is between this ellipse and the circle, right? The length of the same major axis we shall call as small a. So this CA is small a, and CA prime obviously is also small a. And then distance CS is then becoming AE, right? Now taking A prime as the x-axis and BB prime as the y-axis, if I look at the equation for the ellipse, it can be written down as x square by A square plus y square upon B square equal to 1, right? Where we have set B square equal to A square into 1 minus E square, right? This defines kind of the minor axis over there, semi-minor axis over there, okay? Now, due to the inherent symmetry of the ellipse, there has to be another focus, right? So that is going to be S prime, which is exactly the reflection of S on this particular C, right? Now, the other important properties of ellipse is that if I consider any point on the ellipse, then the distance PS and PS prime, which is the distance of the point P from the two foci basically, and the sum is always going to be twice A, which is nothing but A prime actually, right? So this is actually, this can be used, this property can be used to draw an ellipse by using a string actually. We can take two nails, fix them at 2 points on the table, for example, take a string whose length is more than the distance between the nails, and then take a pencil, keep it taut, and move it around the table. You will actually generate an ellipse over there, right? There is also a reflective property of the ellipse actually, which is not very much useful as such, but it is interesting to note. If you just send a ray of light from the one of the focus S, then after getting reflected at the point P on the ellipse, it'll actually pass through the other focus by the right. So we can design, or in fact, historically there have been designs of whispering galleries, for example, where the gallery is in the shape of an ellipse. So if you whisper at one of the points when the focus actually, the person or the other focus is able to hear you very, very clearly, in fact, right? This was one of the properties of the ellipse which are being used over there, right? Now the ellipse can also be obtained as a locus of a point whose distance from a fixed point S, as usual, which is a focus, it bears a constant ratio less than 1 from the distance or to the distance of this point P from a fixed line. So basically PS upon PM should be a number which is a constant, and that constant is less than 1. Then also you're going to generate an ellipse actually, right? This is in fact how the conic sections are usually defined over there, okay? The other interesting thing to look at is the fact that we can actually obtain an ellipse by rotating or by projecting a rotation. Basically, take a circle. Suppose I take a circle of radius A. So let's actually look at this particular thing. Yeah, the recording and session slides possibly later on available, by the way. Okay, don't worry much of that. Okay, so let's try to look at the whole thing in GeoGebra again. We're going to consider as a projection. So I'll discard it. So what we have over here is a 3D kind of window which is actually available in GeoGebra. There's a way that you can actually visualize planes, surfaces, and so on. Now over here we have actually a circle. Right now we can just, for example, remove this. So we have basically a circle, right? This is circle on the XY plane. Now what I have over here is I'm going to rotate this circle about one of the diameter. This is the diameter about which I have turned or rotated the whole circle, by the way, right? Depending on how I have chosen the angle. Now, if I project this circle back onto the original plane, so I'm trying to just project it back, right? Implies basically drop a perpendicular from any point or every point of this particular rotated circle back to the original plane, right? So what I have done is I have actually looked at, or maybe you can just see, for example, slightly we have in this case a point P and there's a projection over here. This is what I mean to say when I just project it back. In this case, if I move the points, what I actually end up getting on the base over here in the original plane is actually ellipse, which looks like a circle over here. But if I can just move up over here, in fact, I can remove this projected or the rotated, circle, and just look at the projection that we have got on the original plane. And if you see, this is actually turning out to an ellipse over there, right? So by determining in this case the angle by which we have turned the circle, we can actually get an ellipse of any size over there, right? So this also is very useful in getting the area of the ellipse, by the way, and we shall see. Hopefully that is clear enough. So going back over here, if I consider this projection, okay, so yeah, right. So if I look at the same thing. So we have this circle of radius a. I've chosen the radius to be a, and we rotate it about one of its diameters, fine, by an angle which I've chosen to be cos inverse of b by a. B is some number less than a, right? Then the rotated circle, if I just project it back onto the original plane, which I've done the red one over here, then the projection is an ellipse, which we just saw over there, okay? And the semi major axis is a, and the semi minor axis is b, which is what we have over here, right? Now, normally what happens is the areas they project as vectors as well. You can actually find out the area for the ellipse, therefore, by projecting this blue circle back onto the original plane. So because the area project pretty much same as the vectors, I could therefore obtain the area of the ellipse by looking at the area of the circle, pi a square, projected back to the original plane. So I get cos phi factor. This is how the vectors are projected, right? So pi a square into cos phi then gives us pi a square into b by a, which is actually pi ab. That becomes the area of the ellipse, which is nothing but a bigger circle upon the, we have the bigger diameter, radius rather, and the smaller radius, right? So this is one way that you could actually obtain the area of the, the ellipse actually. As it turns out, the length of the arc of the ellipse is not obtainable actually in closed form, okay? It gives rise to some kind of integrals referred to as elliptical integrals, which are new functions in themselves. We cannot find the length of the ellipse in a closed form over there, right? Okay, so if I look at a bit of history, by the way, mostly it is this history is with to do with Johannes Kepler actually. Usually, say before that we know that the Greek geometers, they studied the conic sections of which the ellipse is one of the part actually, as say conic sections over there. So that is, I didn't mention it. In 1602, which is quite recent history, around 400 back, Johannes Kepler, who was studying the orbit of planet Mars, he wrote to Danish astronomer Tycho Brahe that he believed the orbit to be an oval actually. That was his, normally, Kepler was trying to find out, he was a bit before Newton. So he was trying to study the planetary orbits, okay, and try to find some pattern in them, right? He, as maybe many of you may be familiar with that, he gave three laws actually, which are referred to as the Kepler's laws. He realized later that the orbit was actually not an oval, but rather an ellipse actually, with sun at one of the focus. And this was published in 1609 actually, right? Excuse me. However, Kepler was unable to account for this result, as well as the other planetary laws that go by his name theoretically, okay? Just a moment. Try. So it was left to Newton actually to prove them, right? As we all know, Newton actually was able to prove it by using his law of gravitation and the integral calculus that he invented. He was able to prove this result in 1680, by the way, right? And you can actually see the, the kind of might of Newton by noting this fact that while Johannes Kepler gave the three laws over a span of around 20 to 30 years, by the way, Newton was able to prove the whole thing in only one night, actually, right? So that was the power that he had because of the integration of mathematics with physics, in fact, right? With the gradual acceptance of Copernican, heliocentric model, we know that originally very early people used to believe the Earth was centered, geocentric model. But with Copernicus, the model, he actually proposed a heliocentric model, and people were gradually able to accept it. And also the rotation of the Earth, for example, it was believed that Earth is an ellipsoid, okay, which is a solid of revolution, in fact. However, Maclaurin in 1742 actually, he proved that a homogeneous mass of liquid, which when revolving uniformly under the action of gravity, would actually take such a shape over there, right? This is what was done for a bit of historical fact. Also, it turns out that, we might be familiar with this fact that if we take a lens, for example, a spherical lens, and we focus it, we just focus a beam of sunlight. And usually, it is assumed that a convex lens or a spherical lens is able to project or focus the sun rays at one point, right? However, this is not actually true. It turns out that if we want the, a lens to actually focus the sunlight at one particular point, it needs to be an ellipsoid actually. It is not as sphere as we might believe, but actually sphere, ellipsoid, which is nothing but a solid of revolution that we obtain by revolving the ellipse about one of its diameter. Okay. Anyway, so the next one that we take up, and we shall be very brief for the rest of the things, by the way. I will not take very much of time because already maybe you can just do it sometime later, but I introduce basically a few of the curves and that'll be all for it. Okay. So the next one is a cycloid, by the way. Okay. Now this is very interesting, by the way. The idea is that if we kind of take up we have a wheel which is turning, which is moving, right? And then you take up any point on the periphery, then as it moves over there, it actually traces out a path, which is in fact a cycloid over there. We shall see that in a minute. First of all, the diagram that I have drawn over here, it is just drawn by using a circle can be drawn by using compass. So to do a bit of work, we draw a number of circles, equally spaced, right? And also the equally spaced radii is what I need to draw actually. So when I just draw such a number of circles as well as their radii, then let us just switch by the, yeah. So what we have is, I have in this case a circle and there's radius. So I have just in this case arranged for a number of circles to be drawn with their radii. And when it is done, what we get is a series of diagrams like these, right? Oh, sorry, I think I didn't, just I forget. So I forgot to switch the presentation. Just a moment. Okay. So I'll do the whole thing again. So what I have over here is, there is a circle. Okay. I'm arranged to draw a number of such circles and their radii, okay, equally spaced. And let us see what we have over there. We have this series of circles with the radii. Now look at the points which are the points on the periphery of the circle at the end of the radius, right? For example, this point, I'm looking at this point over here, these points which are end of the radius and lying on the periphery. So if I look at their, their path, the trace, by the way, then what I end up getting over here is actually this red curve, which is in fact a cycloid, right? This is cycloid. This is not exactly a sine curve, for example. This is not a cosine curve, but a cycloid over there. In fact, if I consider, for example, as I said, a wheel which is rolling, in fact, I might show it over here. A wheel, when it rolls on the ground, for example, it actually generates an ellipse over here, right? No, sorry, I'm cycloid over there. And interesting, this is also one of the many ways, oh, this is pretty bad, to generate actually various curves, right? Now, it turns out in this case that many curves can be actually obtained by moving circles or other kind of, curves on a different curves over there, right? In this case, why cycloid is, I have just concentrated on it, will be clear in a moment. For example, in this case, starts to trace out a certain path, as you could see, as it moves over here, it actually traces out a path which is in fact a cycloid, right? So this is effectively a cycloid when a wheel rolls on the ground over there, right? Now, this particular thing as such, it actually possesses quite a lot of things, a lot of properties, but I'll be very brief and just talk about, two of the important properties over there, which is what we have, and some very fun fact over there, okay? If we consider, for example, such a cycloid, what happens over here is, it has two properties which are important. One of them is called a tautochrone, right? Interestingly, what happens is, if you consider, for example, this particular curve, and you just make them inverted, flip it, so the cusp is pointing in the upward direction. In that case, if you release a point from any point on this cycloid while it is inverted over there, starting from any point, it will take always the same time to reach the bottom, which will, this point will be actually be, right now it is the top, but it will become the bottom when I invert it. So no matter where I start a particle from, it will always take the same amount of time to reach the bottommost point actually, right? The other thing that is of importance is basically the brachistochrone property, which is actually saying that if I have a slide which is shape of this cycloid over there, and you allow a particle to slide from the top over here, then it's going to reach the bottom in the minimum possible time actually, right? This is not going to be for any other curve, but for this cycloid over there, right? The other few things, by the way, for example, we already know that, for example, pendulums that we have over here, pendulum time period actually depends on it depends on the amplitude, right? If I have a very small amplitude, then the time period becomes independent of the the amplitude, but otherwise it will depend on the amplitude. However, if we force the string to trace along the cycloid, interestingly turns out to be independent of the amplitude actually, right? So basically, if I have a inverted cycloid and at this corner I'm able to suspend a pendulum, then irrespective of how much I deviate it, it always move the same time period, in fact, right? That's one of the interesting properties. Other things, like a fun fact, for example, if we have a square wheel, for example, if I say that we have a cycle, but the wheels are not circular, they're squares, right? Then interestingly, if I have the road in shape of a cycloid, suitable size over there, then the cycle will be able to move on that road and you will not feel a jerk actually, right? I was unable to, have this whole thing animated, but at least can be done over there, right? So that is one thing that we have. I think that mostly, instead of, because already short present time, I'll just show you a few more of the curves and the way they can obtain them, and hopefully you'll be able to explore a bit, right? There is something called a cardoid over there. This can also be obtained by moving a circle. You basically draw a circle. This dark circle is a fixed radius. That's a fixed radius. And then we just take various points on the circles and take this fixed point at the corner and keep on drawing circles centered at that variable point and having radii as those things. Let's see that we can again have this particular animation over here. And that should be okay. I cannot. Just a few more minutes. I believe that should be enough for us. Right. So I'm going to open one of the, where it is. I think that maybe this is okay. I was unable to save it for seems, by the way. Okay, cannot show it right now. However, so you can explore a bit, but by the way, or maybe you can just do it sometimes later if you want. I'll share you the construction at least, that I can do later. But over here, for example, this is known as a cardoid. I said that this can be obtained as locus, envelope rather, of all the circles whose centers are moving on the circle, but the radius is always equal to that point from this fixed point, which is on the left corner over here, right? That's a fixed point, and the other point, which is center of the circles, will be moving on the circle. You generate a cardoid like this, right? Other curve that we have is referred to as an asteroid. This can be actually very easily generated if you allow a line of fixed length to slide on the coordinate axis, for example. If the line of a fixed length is allowed to move along the coordinate axis, for instance, what you generate is known as an asteroid, right? The equation is something like x power 2 by 3 plus y raised power 2 by 3 equal to 8 power 2 by 3 actually. Interestingly, if you allow the area to be constant, not the length, then what you generate is actually a hyperbola, right? And if you allow the length of the intercepts to be constant, then you actually generate a parabola, by the way, right? And there's this last curve that I would like to, just so that you can know the name of it, referred to as nephroid, by the way, right? Looks very much like levers, that's why. This nephroid is actually obtainable in two ways. You can actually, oh, sorry, kidney, by the way, not livers, sorry, it's kidney. But you can actually obtain this particular curve in two ways. You can allow a circle to roll outside a given circle, fixed circle, the black one. Alternately, with the black point or this, we have a fixed circle, this black one, and what you do is you take up points on this circle as centers and try to draw circles which are going to touch the vertical diameter, right? This way, what you end up getting is this particular envelope is going to be this nephroid that we have over here, okay? So I think with this, I will end for today's session, by the way, because it's already too much of time. So the idea is that I hope that you are able to, follow a few things, and if it has piqued your interest, for example, you can explore them a bit more, right? There are many, many other curves which I obviously cannot cover in one of the sessions. Hopefully, you can actually go through a few of them. Okay, so that will be all. Thank you, everyone, and if you require some questions, any questions you have, I can just take it up. Okay.
Yes. So anyone have any kind of question can ask to Anand. This is a question answer time. Yes. How he generated on how he used GeoGebra, or what is the history we have done and the uses we have seen, the envelopes and all those related to that. If you have doubt, you can ask.
Well, at least even if you enjoyed the whole thing, then I hope that
What's real? It's really great and amazing session. Thanks, Anand. Yeah, it's really good to know it.
most welcome.
Anyone? No?
It may be so that people are still to. Well, if anybody has any question, you can always take it up. You can type it as well if you want. Yes, Harsh, go ahead.
Yes, Harsh. Yeah, even just unmute and can tell even.
I think just typing the whole thing out. It would be much useful if we just unmute and just send the question, isn't it? Oh, the concept of ellipse. Well, as a concept, the ellipse is, you can think of the ellipse as just a flattened out circle, by the way. It turns out, the planets, for example, like the Earth, other planets in solar system, they're actually moving in elliptical path. The path which take up is not exactly a circle. However, they are very, very close to circle, by the way. Okay, say extremely close. In fact, if you look at the eccentricity, which tells us exactly how much the planets deviate from the circular path, they are very, very small. For Earth, for example, is extremely like 0.09 something, right? Very, very small eccentricities. As a concept, ellipse is nothing but a flattened out circle, as simple as that. Okay. Say, though it has a lot of other mathematical properties, but it requires rigorous proof over there. Okay, it can be done, and coordinate geometry, actually analytical geometry, has made it or enabled many of the properties which are very geometrically obscure. It can be actually done in a very simple way, not exactly elegant, but at least it can be done, right? That's all I can just say for you. The equation is known. If you want any resources, I can point out, and you can just go through that. Okay. Yes, Sarfraz.
Sir, I had a question and I have a question right now also.
Mhm.
Do you, because of the sir, I have listened many times that the planets move in a elliptical way.
Yeah.
But why does this happen, sir? There is simply the more circle is the more simple way to move, sir.
Yeah, definitely circle is a more simpler way to move actually, but seems like in this case nature is not preferring a simpler way. In terms of mathematics, you can actually prove it by using Newton's laws. It turns out the any force which is an inverse square law actually, like 1 by r square, which gravitation is, then the general path that an object can have in that sort of force field is actually an ellipse. It's actually a conic section. It's not only an ellipse, by the way. It can be elliptical, it can be circular, it can be parabolic as well. You know that, for example, some comets, they come from very, very far away and they move in a parabolic trajectories. In fact, like Halley's comet, for example, whose time period 76 years, it's actually an elliptical path, which is a very elongated ellipse, right? In general, the path are not always ellipse, but it's more like a conic section. Okay, And it turns out that whenever the total energy is negative, only then it is going to be ellipse actually, right? In general, it's ellipse, but this can be done. It turns out to be the situation by using, because of force laws actually, the way that the forces act between sun and the other planets. That is the reason why they turn out to be the ellipses actually. Okay.
Sir, when we think in a physical scenario, sir,
Yeah.
over there we think that the center of the universe, center of this
Solar
galaxy
system,
is
galaxy.
galaxy is like, sir, black hole, and the center of the solar system is
Yeah.
sun. And when something move around this one center, it could it should move around a circle like, sir.
No, no,
But
it should not. I mean, say it's not mandatory. It actually depends on the force laws, actually, right? Everything has to deal with the causes, and the cause in this case is a force. Okay, it can give rise to circle, definitely, but it can also give rise to ellipses. You should notice,
yes,
for example, that the planet of the Mercury, for example, the path of Mercury is not exactly an ellipse, by the way. It's in fact an ellipse which is turning its major axis. So it's not in fact even a closed path, actually, right? So there are some kind of exceptions, but they're all explainable by using the general laws, actually, right?
yeah, sir. I think some of the different forces is responsible for such kind of movements, sir.
Well, so not some different kinds, but kind is always the same, gravitation, but just
Yes.
many other particles are there. That's all. So multi-particle system is going to be complicated.
Okay, sir. Thank you, sir.
Yeah.
Yeah, about how to develop advanced reasoning. Okay. Yes,
It's
sir.
a very
Thanks. Good to you answer. It's really good.
okay. So this is actually solve difficult problems. How to see multiple perspectives, same concept. Well, this is a very generic problem. By this actually has to, well, I mean, at least if we stick to, I mean, say if we just consider in context to what, not maths, but in general, the, this mathematical learning or any kind of learning, by the way, one particular way to develop advanced mathematical reasoning is to look at advanced problems, or at least first begin with smaller problems or simpler problems, and then move over to the advanced problems, right? This is not only going to be useful mathematically, but also in other things. Even in programming, for example, you can first break up the whole thing into little pieces, divide and rule policy effectively. That's one particular thing that you're going to have. Regarding perspective, the idea is to develop, I mean, say, one way is to actually look at other people solving, how they do that, okay? Discuss with them, that's one more thing. Read books, that's one other thing, actually. Everything will going to take some time over there. There's nothing which is going to be overnight, but overall or gradually, you need to develop a sense of something called a vertical thinking, right? You need to look at the bigger picture and how it is connected with the smaller parts. Very abstract idea, but then that is the usual thing that you're going to have over there. It takes some time. Machine learning is all about this whole thing, by the way, right? You have to just consider in this case exactly how this particular things are being developed by looking at smaller parts and then try to generalize over a bigger path.
Correct. Yes, right.
That's what I can say, right?
So, this my whole machine learning is based on that. You see just
Exactly.
small thing and slowly develop, algorithms are, just small thing and develop the algorithm. So,
Exactly. I mean, so even how the little children they learn by the same thing over there.
yeah. Okay.
Okay, so anything else?
Yeah, thanks everyone. Anyone have any question
The
still?
time
You
is
can ask.
already.
Yeah. Okay. So thanks everyone. Thanks
Thank you.
for joining. I hope you enjoyed this seminar, this presentation. And once again, if you want to present, okay, you can just ping me here already. Sharing the many times C form. Just ping me. You can tell us your idea, and we'll
Yeah, yeah,
our core team member Anant is already there. He will really help you. And any area is is really good. So
yeah. I'll try to help as much as I can, either. Okay.
yes. So please let us know. Okay. Thanks everyone.
Okay.
Okay.
Thank you and good night, everyone. Yeah. Thank you, sir. Yeah.
Yeah. Thanks, Anand. Thank you so much for great this seminar.
Thank you. Okay. Okay, we should, let me just try, and I'll just maybe we'll share with you the entire thing. I mean, some kind of heuristic in problem solving in the G space, right, which has been created over there. We try to